got questions? No? Anybody got any questions?
I just couldn't find.
I didn't see an answer, so I didn't see an answer.
Yeah, for the trace question.
Okay, so
For like
if
ABC is equal to AC. C80. True. Slash one. Is that a fact? Or I think I found it.
So count that. So we know 0, that's 1, 1 is 3.
And 0. That's why you're recording.
It's got to be a good day. Every day. Yeah, it's true. Not
a good day with coworkers who have no idea about physics trying to tell you time travel exists. I listened to a 1-hour rant at 4 o'clock in the morning at work. Why?
They want to say that they can time travel.
Yeah, because he apparently watched these lectures online. And so he knew more about physics.
You know, some people just gotta let them have it.
Oh,
It's not worth the fight,
I wonder.
especially at 4 a.m. It's really not worth the fight.
It wasn't.
I wonder, Dr. Dobbs, anyone ever try to lecture you on physics?
That's just so funny.
And they didn't know you're a physicist?
Well, he saw me with my physics homework and he started talking about the random videos he watched online and how time travel exists and all this crap.
Someone tries.
And he tried to talk about string theory and
Oh, yeah, because he goes, yeah. What is that supposed to be? I heard. What is
Yeah,
that?
so
What is
you
so-called
switch it.
string theory?
Yeah, so the fundamental particle, like an electron, we haven't found any structure yet. We don't even, it's smaller than anything we've been able to measure. But the string theory is a hypothesis that those particles are actually have some structure to them called strings. And, but they're kind of a string theory. And it deals with big scale so small that it's very difficult. I mean, with today's technology, it's impossible to verify.
And when you say structure, what do you mean by structure? looks like. Like, how the mass distributed is?
How the parts,
Or how the parts are distributed of the.
what kind of parts and electrons we have.
So it's not a ball.
What's that?
It's not a sphere.
It's not, I don't know what it is.
Could be a donut for all we know.
That's Monday, we can't do that.
Honestly, finding out would be like, you could attract a lot of people in science with that.
When the electron looks like a donut?
Yeah.
Oh, yeah, dude, that would be everyone's.
And then the other two months, we can't do it.
Eat a lot of.
And then on Tuesday,
Part of these like
I'm
that.
like, I missed the test and speech.
Little electron donuts.
Yeah, all electron donuts. That's what, so we're just transferring donuts when we,
Donut to donut.
donut to
That's what
donut.
quantum is.
Can I ask you another word? What's the basics of quantum entanglement?
And so.
Yeah, so we
we all
only dealt with
pick
those
numbers,
particles
that's
at
how
the
we
top.
put groups.
And,
And then we
so,
pick numbers.
I am gonna give a talk actually next class.
Because the 22nd is each.
It gets on to quantum entanglement. You have two particles, like two electrons in an atom. That's the helium atom. The wave function describes particles and the guiding wave structure that comes out. And so you can, in fact, create situations like two particles, which were interacted at some point, but then separated. The entanglement means that there's still some influence between particles, between these two electrons, even though they've been separated.
Because of the guiding way.
What's that?
Because of the guiding way.
But it involves, so there's some interesting experiments that were started on an idea by Einstein. PFR.
Oh, no.
Take two electrons, interact them, take them, separate them, and you do a measure on one of them. Here's the influence in some way. What's going on with the other?
That's cool.
Yeah, so it must involve some kind of superluminal interaction, something faster than light. The only reason why details, again, because we don't understand the guiding structure, we don't know about how that works. Yeah, and so it's all contained in the Schrodinger equation for two particles. We can start to understand the subject. I think that's chapter 8. So you might start reading chapter 8 if you're interested in entanglement. You're reading won't really have enough time to go into it.
Wouldn't have enough knowledge to test that.
Yeah, you should. You have enough now that you could start reading chapter 8. So let's see, there's a little bit in chapter 5 on notation, and then you might use in chapter 8. So there's maybe some notation in chapter 8 familiar at the beginning of chapter 5. A little bit in chapter 5 that sets you up for chapter 8. Most notation. So that's in the book. So if you're interested, and he goes into quite a bit of depth on the PFR experiment. A lot there. Very interesting. Okay, so we have a test on chapters 3 and 4 in class next Monday, and then you have your Thanksgiving break, and you get back last week. After Thanksgiving, we'll just study for the final. Fine. There's a practice test on Canvas, in a separate folder. Anyway, that will help you to prepare for the test. Practice test is long and got lots of problems. So if you know how to do all those problems, then you'll be okay. I'm going to select something either very much like one of those problems or something like that. Be much shorter than the practice test. So, much shorter. It'll be an hour, right? Practice test may take you more than an hour. Probably will work it all through. So there's no homework for Monday, but you might want to start looking at the practice tests now, so you can ask any questions you might have. Right?
Are we gonna go over it like we did the last test?
No, but it's take it from homework, everything and the text. So you study the practice test, and then go back to the problems of homework that we send out solutions and discuss. So I think it'll be okay. Be a good idea to at least have a look at that now, so that you can. I'm not sure how you would even go about doing it. Completely confused on something. This would be this week, ask in class on Wednesday or Friday. Friday would be especially good day. I don't think I have much planned for lecture on Friday. Field questions. Okay, so we're going to start the subject of angular momentum in quantum mechanics. And we're going to use what we've developed last couple of lectures and homework. So we had a case with spherical symmetry, and there are two simple examples of that. One is just to put a particle in a sphere. The particle in a cube, but suppose to put a particle in a sphere so that it's contained inside of the sphere. Another problem where this comes up is the hydrogen. When the potential energy, you have a proton at the center, and then you have an electron orbiting around the proton. The potential energy is just 1 over r. It's the phi field, the electrostatic potential. It's just 1 over r. This is similar to gravity. Gravity is similar. Just the potential energy goes like 1 over r from the center of the Earth. So the moon has potential energy that goes like 1 over the distance from the center of the Earth to the moon. So I guess you could say also this would be considered the quantum mechanics of the Earth orbiting the moon. The moon orbiting the Earth. But of course, well, I guess we could do that. We could set up a Schrodinger equation for the moon orbiting around the Earth. Formally, it would be the same. Okay, so angular momentum in a case like that, like the moon orbiting around the Earth, or the electron around the proton, or even the electron just moving around inside of the sphere, the angular momentum should be conserved because there's no torque acting on the particle. Right? The force, in this case, is directed back along the line. So we have a proton here, we have an electron orbiting around it. Negative charge attraction to the force is radially inward. You remember the torque is the force F, and R is radially outward, F is radially inward, so there's no torque. And from our Newtonian mechanics, that means the angular momentum is conserved. If the torque is 0, then the angular momentum is conserved. So now we want to understand how this works in quantum mechanics. How does angular momentum work from the Schrodinger equation? Okay, so we have an operator which we can form, which should give us the angular momentum, which comes from the position and momentum operators that we developed before. So we have now the gradient operator here. So the momentum minus I a bar times the gradient. The gradient, remember, is just the operator, which is the derivatives in each direction, like this. Writing it down in Cartesian form, write it down in polar form or spherical coordinates and so forth. It's not important for us to do that at the moment, but this is how you would define an operator relating to angular momentum. Okay, so we want to study these operators, and it's really interesting. It turns out to be quite a bit more subtle than you might expect. So the z component of this then is going to be y px minus x py. Right, so px you're familiar with. Y is just the derivative with respect to y. Okay, so here's this operator. Now remember, we were cautious. We learned that x and px do not commute. Stop writing hats on all this stuff. These have hats on. Okay, except a bar and I. So these p's especially are derivative operators, and this is going to act on something. Remember, when I write operators, there's always the implicit. It's always implicit that this is an operator that's going to act on some function. So these are derivatives, and they're going to act on something to the right.
X and Y are operators as well.
Yeah, that's right, but they're kind of trivial operators. If the wave function is expressed in terms of the x, or the position, x, y, and z, then the x, y, and z are operators, but they're trivial, because x times a function of x just is x times a function of x. Okay, but y should commute with px. Right? Because the y should commute with the derivative with respect to x. And x commutes with py. So the order here doesn't matter. You might think, well, wait a minute, if I have position and momentum together, then I have to be careful about the order of this. Because x and px don't commute, but you don't have a combination of x with px or y with py or z with pz. They're always with other coordinates here. Y with x here. Okay. So this is then I can write this as minus I h bar y times the derivative with respect to x minus x times. Okay. So x and y commute with the derivatives of y and x. Okay, so far? Okay, but let's write down Lx. Y dp minus dpy. Okay, also, there we have again combinations that commute. All right. Okay, so far. But notice that we'll find out here very quickly that Lx and Ly do not commute with each other. So let's see how that goes. Work it out. In fact, I'm going to give you the answer here. Let me just write down the answer. Make sure I get the sign correct. Very interesting. Commutator of x, Lx, and Ly give you Lz. Let's see how this works. So we just take our definitions here. Okay, and we can prove that one of the things inside the commutator is a sum of two operators. Then I can write it as a sum of two commutators, each for A and B. This is easy to see. You just write down the definition of this. It's A plus B minus C times A plus B. I can regroup the terms AC minus CA plus BC minus CB. And then this is this commutator and this is this commutator. Okay, so in other words, I can take this and make it into four commutators. This one and this one that I want to do. This one. Okay, and so examining this, the z commutes with px and py. I write out this commutator zpy times zpx minus zpx dpy, but the z commutes. So I can, in fact, bring out the z part here. Let me write this one, zpy dx d squared. commutator on px. This is the derivative with respect to y. This is the derivative with respect to x. And the partial derivatives, the order of differentiation doesn't matter. I have a mixed second derivative like this, operating on some function. It doesn't matter whether I do first x then y or first y then x. So this commutator vanishes. So this one is 0. This one looks a little different, but it gives the same result. So the x and y combined here can just pass through the derivative with respect to z. And I get the commutator of z with pz, which is 0, right? Twice minus pz twice. That one's also 0. Okay, that's nice. Things are looking up. So we're left with these two. Let's do these. I'll write it out here. Okay. Now these y and the z here. Let's see. I have. Let's see. I want the y and the px, right? The y passes through all of this. This y commutes with all of this, and the px commutes with all of this because there's no x here. So I can pull out the y and the px. And get pz even with z. And that's like what we wrote before, except it's reversed. So I could multiply this equation by a negative sign. Commutator px with x is negative I h bar. So this is negative I h bar. Okay, so that's the let's see, that was this term. Now we're going to do this term. Okay, let's see. I want this one. CPY XPZ. Okay, and the Z, so let's write it out. ZPY XPZ minus XPZ ZPY. Okay, the PY commutes with everything all along here, and the X commutes with everything because there's no PX. So I can pull out the PYX. And this is the commutator of Z PZ, which is then IH bar. Okay, so then we put it all together. We have two terms here, LX with LY. Then we get this first term minus IH bar YPX. We get plus IH bar QYX. See that? Yeah. Oops. Yes, there we go. Now let's see, I have a sign. Yes. The sign wrong here somewhere. And I know this is correct, so this should be. I'm getting this is not LZ but negative LZ. I'm getting a positive sign. mess something up. Okay, so I'm sorry about that. Negative. Don't know why. Did it this morning. Now I can't make it work.
So what you're saying is LZ is YPX plus XPY?
If you remember the order of operators, but the order of things in the cross product. R cross P.
Oh,
P component is going to be Y PX minus XPY. Negative signs on one. Oh,
Those two
did I do it
parts.
right? Oh, I did it.
yeah.
There we go. Okay. On the board for some reason. Okay, it came out right. Seems right. I know the negative sign is correct. Okay, so the important thing is that LX and LY do not commute. Well, that's kind of strange. We have to go back, remember. So first, let's spell out all these different cases. 0. Y with LZ, minus I, X bar, LX, LZ with LX, LZ with LX. Not 0. Okay, so let's go back to the end of chapter 3, where we were looking at commutator relations. Remember, we said if two operators commute, then we can have a set of functions which are eigenfunctions of both operators at the same time. When they don't commute, there is no set like that. The failure to commute means that we cannot have the eigenstates of both operators. So that means that the wave functions that we were looking at, wave functions, remember we solved the angular part of the wave function, spherical coordinates, broke it up into two parts like this. That means that these cannot be simultaneously eigenfunctions of all three components, Lx, L5, and Lz. Strange. And the other thing was that if it's an eigenstate of a function, then the uncertainty, the standard deviation over an ensemble, is 0. So in other words, we can't have an ensemble where all three components of the angular momentum are well defined. That is, where there's no spread over the ensemble. Say that again. Cannot have an ensemble where the uncertainty in Lx, uncertainty in Ly, uncertainty in Lz are all equal to 0. Can't do it. In fact, your ensemble can be an eigenstate of only one of these three operators, not all three, but just one. You can pick one, then you'll have uncertainty in the other two. There will be a non-zero standard deviation. If I prepare an ensemble in this state, I tell 1/3 of the members to measure Lx, 1/3 to measure Ly, 1/3 to measure Lz. The best I can do is to get one of them to be 0 by choosing an eigenstate of Lz, for example. That's the normal convention. Then Lx and Ly measurements will come out with a width to them, a standard deviation. There's no way to prepare a state where Lx and Ly are uncertain. So the other operator that is the magnitude. This. Okay, we find out that this operator, which is the magnitude of the angular momentum, used individually, Lx, Ly, or Lz. But because these don't commute, only resolution is the following. I can form an eigenstate of Lz and L squared. So I can find eigenstates of L squared and Lz, but not then Lx and Ly. Constraint. This has to do with the stochastic nature of the guiding wave. Remember I said there was no torque, but that's just from the attraction of the electron to the proton. The guiding wave is knocking things around, causing torque, and can be causing deviations in the angular momentum. So how does that work exactly? So I'll get into that here in just a minute, but just to finish this mathematical structure, these functions, YLMs that we constructed and saw in the book, are already eigenstates of L squared and Lz. They're not eigenstates of Lx and Ly. That means there's an uncertainty in Lx and Ly. There's going to be some spread. So looking at L squared acting on the YLM, and then Lz. Okay, so those functions that we wrote down are already eigenstates of L squared and Lz. They were constructed that way. Didn't tell you what was going on. That they were chosen to be eigenstates of both of these operators. And notice that the eigenvalue associated with L squared is the L quantum number. It's related to L. And the eigenstate of Lz is related to M, the other quantum number. So we can use those two numbers to represent the states. Remember the S and the P and the D states. So to review that, we have these different L and N states. N ranges from negative L to plus L. So if L equals 0, there's only an N equals 0. If L equals 1, there's 3 values of M. If L equals 2, there are 5 values. So this is called S, these are P, these are D, F. So these were already constructed to be eigenstates of both L squared and L. But we have this unexpected part. I mean, that's good. That's good. We have this unexpected part that can't be eigenstates of Lx and Ly or Ly. We've already got it down to as tight as the ensemble will go. It's a kind of uncertainty principle in a way. Not expressed in terms of the product of uncertainties, but expressed in the way that I was talking about. Okay, so let's see if we can figure out what's going on here. Let's look at the L equals 1, M equals 1 state. One of the P states. And that state, Y11, constants in front of it. Looks like this in terms of the angles. Sine theta times e to the I phi. Pretty simple function. That's one of the P states. Let's operate on this L squared. Well, we get h bar squared times L plus 1. L is equal to 1. It's 2h bar squared. Every member of the ensemble will have this magnitude. for L squared. Every member of the ensemble will have the same squared value of L. So the angular momentum, the magnitude will be the same for everybody. And also the projection along the z-axis will be m is 1. This is just h bar times y1 and 1. So every member of the ensemble has the same projection of the angular momentum onto the z-axis. So this is weird, right? This is the same for everybody. It's an eigenstate. Everybody's going to have the same magnitude of the L vector. And the component along the z-axis is going to be the same for everybody. What's going on? Constraint. I'm going to show you a picture here. I'm going to need to pull this down. All right, here are how the electron, the average motion of an electron in that state, that y11 state. L equals 1, m equals 1. If you go back, remember how to calculate the current and the average velocity. Current operator that you can use for that wave function, besides the y11. That gives you the average velocity of electrons at that point. This is what I'm showing here is the average trajectory of electrons will be going like this. Remember, this is an average now. So there's going to be electrons moving in other directions because of the guiding waves. It's not in the law of course, but the average is like that. Strange. It's like you're going around the Earth, you're sailing around the Earth, same latitude, all the way around. So if you're at the North Pole, you're just going around the North Pole. Don't have far to go. Around the equator, you've got to go all the way around the Earth. Strange orbit. Right? It's not like planetary orbits. Planetary orbit would go around the center. But that orbit up near the North Pole is not going around the center. Right? It's not a great circle. It's a small orbit that's going around. Not like the moon goes around the Earth. Okay, but you can see here, these electrons orbiting around like this. Let's look at, draw it over here. Here's the orbit, like this. I'm going to try to draw it better than that. Here's the proton. There's the electron. It's not circling around the proton. The proton's not in the center of the orbit. Weird. Very strange. So let's calculate the angular momentum of this thing. Right at this point, let's suppose. So the particle's going into the board. So I'm having trouble drawing this thing in 3 dimensions. The side view would be, here's the orbit. It goes around like this. Okay. The velocity is into the board. Here's R. The momentum is into the board. Which way is the angular momentum? R cross P. Get out your right hands. R cross P is this way. Perpendicular R and perpendicular to P. So this should be a right angle here, but it's not. Maybe I need to. Okay, there's L. For that guy at that point in his orbit, this is the average angular momentum for those guys. Right, but now he comes around, goes all the way around. He's coming out of the board. Well, momentum is coming this way now. Where's R cross P? That's the right, this way. So the angular momentum of this thing is, as this moves around this orbit, precessing like this. Around like that. Here, the angular, this is what the angular momentum is doing, right? The end of the vector is on this circle, going around. Okay, now the component, so to do it like I did here, I'm having trouble drawing these things. It's going around. Going around in a circle, right? It's orbiting like this, and I'm drawing it so it's a circle like this. Okay. So the length during this whole orbit is going to be 2h bar, the root 2h bar. 32 h bar. L squared is 2h bar squared. So the length of this vector doesn't change. It goes all the way around, maintains its length. The z component is going to be 1 h bar. This much right here is going to be 1 h bar. That's the component of the angular momentum along this direction. But while it goes around its orbit, it's changing Lx and Ly. Right? These vectors have the same projection this way, but their projection in the x and y directions average out to 0. So the ensemble average of L squared will be 2h bar squared. The ensemble average of Lz will be h bar. The ensemble average of Lx will be 0. The ensemble average of Ly will be 0. They have components in the x and y directions, just the average over the ensemble. 0. Okay, so far, kind of weird, isn't it? Angular momentum in quantum mechanics is strange. And it's the influence of the guiding wave structure. Yeah, Mr. Silva.
Do the averages of Lx and Ly, are they 0 because it's a circle? That's
Yeah. Right.
Are we talking about the actual operator now? Or are we talking about the actual?
Yeah. The operator gives you the angular momentum. So it's the average of the angular momentum.
This is not the average L bar anymore.
Yeah, sorry, L hat.
Yes, it is. The operator gives you the angular momentum in the wave function. Remember, to get these ensemble averages for any operator, let's take Lx. Ensemble average of Lx can be the integral of psi star Lx operator psi. Integrate over the volume of the region. And so the Lx operates on and the wave function, the radial wave function, which we haven't specified, it's not really important. The particles don't change distance from the, on average, don't change distance. Okay, so you just plug this into here, operate with the Lx, which I wrote down earlier. And you do the integral, you get 0. Same thing for Ly. Whereas Lz, this is an eigenstate. So it just gives m h bar, whatever m is. In this case, m is 1. Is 1, this integral, just the integral over the probability over the whole thing. So this is h bar. Same thing is true with operator here. Same thing is true for L squared. Get 2h bars. And I'm just saying. Okay, so I picked one there, but this is true for all of these. They all have this, when I average this thing, this is what I get for over the ensemble. I have these circulating angular momenta. They all average out just the way that I described. It's kind of strange. So it's true for all of these orbits, not just the one I picked. all the members of the ensemble are going to be doing this thing. They're at different places on the different regions. But they all have the same L squared and LZ. And when I average over all of them, they of course get the same L squared and LZ average, but they all have the same. Strange.
You're saying it doesn't matter which orbit you pick right there?
Yeah.
It gives the same angular momentum?
Yes. But same angular, same almost, same L squared and same LZ, not LX and LY, but those all average out to zero.
Right, so if you pick LX, that would just change.
And take LX. So if I go back, I could choose, there were three components of the angular momentum, LX, LY, and LZ, and I chose LZ. It's conventional to choose LZ to be, they don't commute with each other, so you can only pick one. You could have started over all of this by choosing eigenfunctions of LX instead of LZ. And then these things would go around, orbit around the x-axis. And there would be different functions than the ones in the book, different functions of polar coordinates. We chose the polar coordinate system has a special direction. North is special in the polar coordinate system, the spherical coordinate system, I should say. In the spherical coordinate system, the north and south poles are special. And so it's convenient, if you're writing it in spherical coordinates, to choose that axis to be the quantization axis, the one that you pick. So LZ is the one that's where the spherical coordinates are aligned. So it makes it nice and easy to write function. If you don't do that, then it gets messy, but in principle, you can do it.
Why are they special?
Why are they special? Meaning, why are they?
Because you said that the north and south poles were special.
Oh, and the spherical coordinates system. Yeah, because the angle, the latitude, is chosen with respect to the north-south pole.
Okay.
You could have chosen some other point on the Earth for that to start marking latitude and longitude, but it's convenient to do it around the one where the rotation takes out a special direction. Because as you rotate around the Earth, your latitude doesn't change. You know, if you're on the Earth is spinning, and your latitude isn't changing.
Oh,
And the longitude rotates with the Earth, so also your longitude doesn't change, but then the coordinate system has to rotate with the Earth. But in the spherical coordinate system, you're not rotating the other angle, it's fixed. So the spherical coordinate system has a funny thing. There's a kind of, it's got a special point. There's other ways of trying to do coordinates on a sphere. This one is very common, latitude and longitude is very common. Spherical coordinate system is like that. And so it makes it, because we can choose only one, it makes it convenient to choose that one, Z direction, because that's the axis of the coordinate system. Very strange. This is really peculiar. Okay, so this is to illustrate that idea of the angular momenta, or this is the one. All the members of the ensemble will have angular momentum that's in this direction and will cycle around like this. So the average LX and the average LY comes out to be 0. This is it's like L equals 2, little L equals 2. It's not a P state. This is a P state. It's the same basic argument. Yes.
So was all the operator math at the beginning, was that to establish that we can prove this with the angular operators?
Yeah. So notice that, I mean, we had the wave functions there, but the operator algebra tells us that this is the best we can do. That by the nature of the beast, like this, we're not going to be able to have eigenstates of L squared LZ and also LX and LY. We can only pick one of the components to have it be an eigenstate of one of the components. The other two are not going to be eigenstates. In fact, we'll average out to 0. But the LX, the angular momentum, at some point, and some members of the ensemble have an LX and have an LY. that over the ensemble, they're all going to average out to 0. Strange. So in particular, the average of LZ squared will be H bar squared, right? That's because it's an eigenstate. LZ acting twice just gives back that. But LX squared is not going to be 0. It's not going to be 0, even though LX is 0, the average squared is not 0. Peculiar. Really very strange. Now, part of the reason for this you can see from those commutators. Okay, let's remember this operator, PX. Remember, it's the translation operator. Translates functions in X. Okay, then let's look at LZ. LZ, if I write it in polar coordinates, it looks like this. Spherical coordinates. So if this translates in X, what is this? Yeah, it translates in phi. What does that mean? It rotates. It rotates around the z-axis. So px, py, pz translate. Lx, lz rotates around the z-axis. Lx rotates around x. Ly rotates around y axis. Okay. So what does this mean? Let's do this. That does a rotation around x, first y, and then x. And the commutator involves this combination. First rotate around x, then y. So this is saying if I first rotate around the y-axis and then the x-axis, compare it to what if I rotated first around the x-axis and the y-axis? I don't get the same thing.
The opposite side.
Yeah, but I want to take a difference. I want to compare rotating first around x, then y. Compare that to doing first y, then x. Take the difference. Difference. Rotation around the z-axis. This is weird. This is 3 dimensions at work. Connected to each other. If I take a sphere and I have the axes x, y, and z, I rotate a little rotation around x and then a little rotation around y. And so I rotated my sphere. You've got all the points, the geography, all the points on the sphere are marked. Then I do the opposite. I don't remember which I did. But I do it the opposite, or first x, then y. And I compare it to first x, first y, then x, and compare them. And these are small rotations because it's a derivative, right? So this is a small translation. Well, the net result is a translation, is a rotation around the z-axis. This is very interesting. It's really strange. Kind of weird. So you can try this. You got to mark all the points on the sphere so you know where everybody's moving. And you do that combination, take the difference. That difference will give you a rotation around the z-axis. That's what this says. And that's at the heart of the reason why x, lx, and ly and lz don't commute with each other. That's at the heart of that reason. So the algebra gives you that. It's interesting. Not obvious, and it takes a little bit of study to see the significance of this. And he's got a nice illustration in the book. I haven't assigned it as reading. You can see this at work. He does a nice illustration trying to show this from the rotations. Okay, very interesting. So remember, this is just based on the angular momentum, so it's true for a particle in the sphere. Also true for the hydrogen atom. So now I'm going to show you, we'll just take one further step to the hydrogen atom. We're almost there. Remember, this we got from studying the angular part. The last remaining part is the radial part. It's a bit messy. I'm not going to go into it. I'm not having you, he doesn't go through the derivation. Do separation of variables. There are two quantum numbers for the angles. Now you have a third equation in R, differential equation has to be solved. This turns out to have catalogs them in the book. I do have this as reading. Catalog of these functions is it's exponential times a polynomial in R. Complicated polynomial in R, but it's polynomial in R times an exponential. Okay, and there's another quantum number associated with that, which is the n quantum. For each degree, each coordinate, then gets a quantum number. M comes from phi, L comes from theta. This one actually has two quantum numbers here, the same one, L comes from here, and there's an additional one, N. This is called the principal quantum number. N can be an integer. For each value of n, L goes up to n - 1. And for each value of L, n goes from -L plus L. Okay, so I should have specified this is the H atom, this is the hydrogen atom. Where we have the potential energy comes into the radial wave function. The angular wave function doesn't have the potential energy doesn't come into its equation. We do the separation of coordinates. So the potential energy comes into the Schrodinger equation for the radial direction. Okay, so we're almost there. Then. Let's write these down. N, L, M. Every state in the hydrogen atom is characterized by three quantum numbers. First one is N, the principal quantum number. The ground state has little n equals 1. That's the ground state. L can go up to n - 1. So L is stuck at 0. And M is stuck at 0. Because M goes from -L plus L, 0. So there's one of these states. This is called the hydrogen 1s. Ground. And the energy of this is -1 Rydberg. Remember way back in chapter 1, you did a little exercise to calculate an energy scale, hypothetical energy scale involving h bar and E mass of the electron. Combination of these to give an energy gives 1 Rydberg, which is negative 13.6 electron volts. Okay, the next one we go up in value of n. L could be 0 or 1. If L is equal to 0, what values of m can there be? Stuck at 0. But if L could be 1, you can have 3 values of m. So this is the 2s. And this is the 2p. All of these have the same energy. That's 1/4 of the difference. More positive, less down. Ground state's the lowest. First excited is going to be up a little higher. All right, that exhausts the n equals 2 states. That's all there are. Next one is n equals 3. So L can go up to n minus 1. So L can be 0, 1, or 2. And for each L, we have these range of m's. So this is the 3s, the 3p, the 3p. All of these states have the same energy, hydrogen. The energy goes like 1 over n squared. Whatever n is, the energy goes like 1 over n squared. And all of the different states with different angular momentum quantum numbers are the same energy. All of these states have the same energy. All of these states have the same. This starting to look familiar? Yeah, this is what you see in chemistry textbook. A lot of details I haven't given, haven't made you go through all the details, but you see generally how this works. Right? That's what I'm trying to get for you is to see by working your way through the Schrodinger equation to work out all the details, all the wave function and the energy. I haven't made you do that. In fact, he doesn't do some of it, he doesn't do a book. Yeah.
So L is just means you put a P there, or if L equals 1. So L is the one that's determining the letter.
Yeah.
And
The L determines the letter. This is the N and this is the L.
the number in front. This is determined by N.
Yeah. So L equals 0 means S, L equals 1 means P, L equals 2 means D. 3 means.
Well, what is all this?
These are the states of the hydrogen atom. And now, if we go back and we shine light on this hydrogen atom, it can excite the electron from a lower state to a higher state. So the light energy corresponds to the difference in those two energy levels, the lower from the higher, then it will absorb the light. I haven't proven that to you yet. This is the result of Schrodinger equation, putting in light. Or if I start in an higher state, excited state, it can spontaneously jump down to a lower state and emit light, whose energy is going to be equal to this difference in energy. Okay, and this was the big revolution for Schrodinger. He got to this point and saw that he could work out the entire hydrogen atom spectrum that he can observe. He knew he was on the right track, right? Nobody had ever done something like this before. This was new. So he knew something was right. Didn't even know what the wave function was. But he at least figured out there's something real here, something that's corresponding to what's been observed. Don't understand it all yet. He didn't. We understand it better now. But that's the significance of this. This was the quantum mechanics coming of age. This point. When he did this, his head must have blown off. It must have been really exciting to work, spend days and days working out all these differential equations and then come to this. Just must have. What do you do when you do something like that? You're all alone and you understand something that nobody else in the world knows yet.
Don't you scream Eureka?
Yeah, right. It must be really, really exciting. Okay, so we'll see you on Wednesday.